So the backpropagation, a special case of the adjoint method, is a way to compute the gradient. Again, we have an objective function that depends, in this particular case, it actually depends on un, the solution at the nth step of an algorithm. Okay, and then we have u of k plus 1 is equal to a particular function gk of uk. So k goes from, oh, okay, so we also have s, right? Have a bunch of parameters. So k goes from 0 to n minus 1, and u0 is given. Right, so this can be interpreted in several different ways. For example, this can be used to describe an explicit time-stepping method for ODE or PDE, or discretized PDE. Right, so u0 is our initial condition. K is our time step. And my solution depends on the solution at the end of the time evolution. So that's one way to interpret this formula. Another way to interpret the formula is we just looked at iterative methods for solving linear equations. This can be an iterative method, right? And we are just looking at how the objective function depends on the converged solution. My initial condition, initial guess of this iteration is given. This can also be seen as a forward propagation in a deep neural network, where n is the number of layers, and each level you have a compound of a matrix product and some pointwise nonlinear functions. And this u0 is whatever data I have in my training, right? Okay, so the task is to compute the gradient of j with respect to s. So here s is usually not a single number. It usually is a large collection of numbers. So just from the previous example of optimizing an airplane, the parameter s describes the geometry of this airplane. And you can imagine there has to be a lot of parameters to describe the geometry of an airplane. Right? If anybody looked at the shape of an airplane wing, it's impossible to describe with a few words what is the shape, right? It's not any shape you just can recall from your geometry class. So it's usually parameterized as a complex spline surface. And for spline surface, you have all these control points to control how it can move and change the geometry. So this is your S, all the collection of spline control points that defines your geometry. In machine learning, S also you have a lot of parameters. For example, in your matrix, every single entry of the matrix can be your design parameter, right? So this is the task, and once you compute DJDS, you can use it to drive your optimization. There is a number of, in different fields, there are different preferred optimization methods to use. In aerodynamic optimization, quasi-Newton method is usually what we prefer. In machine learning, stochastic gradient descent is usually what they use. So here we focus on how to compute this gradient, which is usually the more mathematically difficult part, and also computationally time-consuming part. So what we do is very similar to what we are doing before, but the first step, we need to linearize it, right? Because this relationship is nonlinear. We want to linearize it, saying that delta j, we first want to linearize this. So delta j is equal to something times delta of un. All right. So this something is analogous to the C transpose we computed earlier. And this something is the derivative of j with respect to un. And if we have an analytical formula for the objective function j, this can usually be derived also analytically. Okay, then what we do next is we go backwards, right? So we start from the objective function, and then we look at what is the last step. Un is equal to gn minus 1 of un minus 1 and s. So we linearize it. Delta un would then be the Jacobian of this last step of propagation, partial gn minus 1, partial un minus 1, times delta of un minus 1, right? And there's something else. Yes, there is also effect of s plus partial gn minus 1 partial s times delta s. So this is the first time we're linking the objective function with s. But there is still a delta un minus 1, so we propagate further backward. So this un can be substituted into this, so that delta j can be represented as a function of delta un minus 1 and delta s. And then in turn, delta un minus 1 can be expressed as a function of un minus 2, delta un minus 2. And also another contribution from s is going to come into this. Right? So this delta un is substituted into the formula of delta j. So delta j is now a function of delta un minus 1 and delta s. And delta un minus 1 has a formula. So delta j can be represented as a function of delta un minus 2 and also delta s. So you can imagine this goes forward and forward, right? But then the formula is going to keep getting longer and longer. Every time I do this, my formula is going to be lengthened by one more term. So at the end, my formula is going to be very, very complex. So is there a better notation for me to use to do this? The answer is yes. So I'm going to use a slightly different way to derive this, but you can see that the formula is going to be a lot cleaner. All right? And this is usually, if you want to derive something for your own formula, this is how I would recommend to derive it. You can do it this way, but like you end up dealing with a pretty long formula. Okay, so another way to derive this, oh, by the way, the very end is going to be, I'm going to be, come on. At the very end, I have delta u1 is equal to partial g0, partial u0, delta u0 plus another contribution of s. So how do I eliminate the delta u0? u0 is given, right? It is not dependent on the parameter s, right? So this is equal to 0. Or in some other cases, u0 is actually a function of s, but it is given as an explicit function of s. Then delta u0 is then another explicit gradient times delta s. So everything at the end is going to be many, many different terms, all multiplied with delta s. So if you just collect all the terms, the collection of the pre-multiplier with delta s is the gradient of j with respect to s. All right. So at the end, you have a contribution from here, and all the way from here, right? But like everything is going to be multiplied with more things. For example, this is going to be multiplied with this because this is delta un minus 1. It needs to be substituted into here. So all the subsequent terms are going to be multiplied with more stuff, right? So you end up with a pretty nasty formula. So I'm going to show you a better way to derive this.